Yes, good morning. Good morning.
Good morning.
Okay, so we will be picking up from where we left as far as the dynamic random access memory is concerned. And I think we did this physically. So can somebody confirm to us where we stopped last time for the dynamic RAM memory? Moses, you are around? You can confirm for us?
As per my note, the last part I wrote was elaboration command. It creates an executable continuity code of VHDL sources Linux. Then we give an example. That's the last part
And
I wrote.
no. We finished with the FPGA and the VHDL. So now we are back to the dynamic RAM uh, sessions, and which we were doing physically. So that is what I want confirmation. What was the last thing we looked at? Or any other person can also assist us. Sefin, you are here? Sorry, Moses, I cannot hear you well.
Sorry, within the DRAM structure, we drew the diagram and we explain how to
How to?
the writing bit of it. Okay, not that yeah. Where we are explaining the math, the RAS and CS and data returns to their.
Okay. So and we did the. Did we do the read cycle? Yes. Right.
Yes, within the real cycle.
And that was our the last thing we did. Sorry.
After real cycle now, that's when we did the structure, drum structure.
Okay. In a way, if we cover the DRAM read cycle, then I think we can proceed with the DRAM refreshing. Just a few notes as we wind up on that. Okay, so we can make a few notes on this. This is our last session on this. So from our previous sessions, we did say that for DRAM, we require a periodic refreshing, and we can note a few things on that. The DRAM cell is refreshed each time a read operation is performed. And typically that periodic refreshing is done is done approximately every 2 to 8 milliseconds to avoid data loss. And to achieve the refreshing, a refresh control logic is necessary. To ensure that then the two refresh modes available. One is we have the burst refresh, and in this case, the normal operation of the memory is suspended, and each row of the DRAM is refreshed. In succession till all the rows have been refreshed. So of course, if the normal operation of the memory is periodically suspended, although for very short periods in the milliseconds range, it still has an impact on the effectiveness of such a memory, and therefore this the burst refreshing mode can lead to slow memory access, and therefore generally can lead to slowing down the system. The other refresh mode available or used is the distributed refresh mode, and under this, that the row the row refreshing is interspersed. Interspersed with the normal operations. So the normal operations are not suspended, but the refreshing occurs concurrently within the normal operations of the memory. And of course, these will be preferred because definitely it will not have as adverse effects as the burst refresh, and therefore this is the widely used in modern systems. So this the most modern computer systems use this mode, that is the distributed refresh. I think we, of course, this is just in summary form, but you can get to read more on that, and you can also investigate further the DRAM technologies, especially on the DDR SDRAM, that is the double data rate SDRAM, and this is what you'll find being used in most of the PCs and in modern computer systems. So starting from DDR1, all the way to, I think, in the market already we have DDR5, and I think probably DDR6 is either released or actually also in the market. And so this is the release date. This was in 2020, and they have their various specifications. So you can read more on this. So what is double data rate? What are the various specifications? Especially of the latest DDRs. So either DDR4, DDR5, DDR6. You can investigate and read more on their specifications and the data rates and the clock speeds involved with that. But because of time, we will not be spending time there because that information is available, easily available. So I would want us to our last session on semiconductor memories is on memory expansion. So that is what we'll be looking at today, expanding the word size, and capacity. And this is necessary because in some memory applications, the required RAM or ROM memory capacity or word size cannot be satisfied by one memory chip. Hence, hence the need to use more than one memory chip. So we'll start with how do we expand the word size. Word size expansion, and we already defined what is a memory word. So just as a recap, if you have you're given a memory chip whose capacity or details is given as that 2x4 memory. What does this that 2 represent? But what does that 2 represent? Yes?
Number of words.
Okay. Then somebody also says number of memory locations. All that is correct. So this is essentially the number of words. What about the 4? What does it represent? Yes, the word size. Okay, that's correct. So this is the word size. In other words, this is the number of bits per word. So in this case, such a memory would store that 2 4-bit words. And we also say that so in this case, the number of data input lines and data output lines would be 4, because the word size is 4 bits. What about the address inputs? How many address inputs do we need for this?
5.
Somebody says 5, and that's correct. And I hope everyone knows where that 5 is coming from. So anyway, I think that shows we have, we can remember what we covered. So let us look at an example. So essentially, the word size expansion is, for example, here you have a memory chip that has 4-bit, can store 4-bit words, but you want to store 8-bit words. So that would mean that you kind of need 2 such memories, that 2x4, so that you are able to store 8-bit words, and in that case you will still store that two words, but 8-bit in word size. So as an example, you want to obtain a 16 by 8 RAM memory from a 16 by 4 RAM memory. So I think it's already clear here that you'll need how many chips of a 16 by 4 to have a 16 by 8. Somebody says 2, and that's correct. So we can just note that down, that since each chip can store 16 4-bit words, and we require to store 16 8-bit words, we'll use each chip to store half of each 8-bit word. So that means we'll need the 2-bit, the 2 chips. So so how do we connect them? So let's maybe investigate this. So the key things we need to determine is the number of data input lines and data output lines, and then the address inputs. So for the data input output lines and for the address inputs, for a 16 by 4 chip, how many data input output lines do we need? How many do we need here? Somebody says 4. And
4.
Yes, correct. And for 16 by 8, how many? 8. Then we come to the address inputs. How many do we need for a 16 by 4? And somebody says Omolo, 4. And for a 16 by 8, how many input lines? Still 4.
4.
And the hope is that everyone is following how we are obtaining this. So I think that is sufficient details that we have to to be able to determine how we can connect those 2 chips, or how we can obtain a 16 by 8 memory from a 16 by 4. And we have determined we need 2 of them. So we can quickly indicate how that connection or that combination would look like. So we have our 2 chips. Well, it's not the best of diagrams, but you can achieve better in the straight lines. So we have our first chip here. This we can call it RAM0, and this is a 16 by 4. And we have our second chip, which is also a 16 by 4. And then we have some control lines. Some control lines. So we have determined that we need 4 input-output lines. Well, each of the chips, in a way, has the 4 input-output lines. And each of the chips also has 4. We have determined that it has 4 address inputs. So these are the address lines. So the question is, how do we connect the various lines? So each of these chips would be storing half of the word, so that in total we can have 8 bits. So our output data will actually be 8 input-output lines. Know how many those are. So these are our data lines, which essentially should be 8. And, Okay, so for the data output, I think that is okay. What about the address bus? We have determined that our combined memory, or the resulting memory, would still need 4 address lines. So here we need 4 address lines. And how are they connected? Once again, we just some direct connection. This is the address bus. And then we are left with our control lines. So how do we connect these? Once again, it's straightforward. So we have the 2 address lines. Sorry, not address lines, but the control lines. So we have the write enable, and so the chip enable, and also from this end we have the same. So yeah, so I think that is that would give us a 16 by 8, quite straightforward. I don't think there is anything to further explain there. So we can make a few notes. So let us look at a read operation for this resulting memory. So if we want to perform a read operation, we have the 2 control signals, the chip select and the write enable. So what should be the status of those 2 control lines so that a read operation is possible? Anybody? What should we drive at the 2 control lines to have a read operation? Yes?
I think the chip select should be driven low, and the write enable should remain high. One.
Okay. Yes, that is correct, Emmanuel, because these are active low. So definitely the first thing we have to enable the chip. So it is active low. The chip select line uh, must be driven low, and the write enable, because we are not doing enable, then we are not doing a write operation, then we need to disable that line, and therefore it must be high. So at least that is the first thing that needs to happen. And yeah, so then for a read operation, of course, the various input output lines will now act as outputs, because they are bidirectional. They can act as inputs and also as outputs. So in this case, now they will be configured as outputs. Then the first chip, that is our RAM 0, places its selected 4-bit word on the upper data bus lines, and similarly RAM 1 places its selected 4-bit word on the low for data bus lines, and by doing so, the data bus now contains the full selected 8-bit word, which can now be transmitted to some other device, and usually a register within the CPU. So I think that combination gives us a 16x8 memory module, which is as a result of combining two RAM chips that are 16x4, and we get a 16x8 memory module. So I think that is clear. So regardless of what figures these are, 16x4, it could be any its kind of sizes. You have an idea of how to proceed and how to finally achieve the word size expansion. So what about the capacity expansion? So look at expanding the capacity, and here when we talk of the capacity, we are referring to the number of words that can be stored in the memory. So essentially, we're looking at how do we increase the number of words that we can store. So if we have a 4-bit, a 16x4-bit chip, and we want to store probably 64 4-bit words, how do we achieve that? So once again, we'll just look at this with an example. And you are asked to obtain a 32 iPhone memory chip from 16x4. memory chips. So once again, because the key things to determine is how many input output lines do you need, for the resulting the memory size, and how many address inputs do you need for the same. So we have 16 by 4. We want to get 32 by 4. So for the data input output lines, how many do we need for 16 by 4? How many data input output lines do we need? Somebody? Yes?
4.
Yeah, we need 4. What about for 32 by 4? How many data input output lines do we need?
4.
Sorry?
4.
4, once again. And then the other one is the address inputs, address input lines. For a 16 by 4, how many do we need?
4.
4. And for a 32 by 4, how many?
5.
5. That's correct. So so we can see, it's kind of the opposite of this, where the address inputs were constant, but the data input output lines changed. But in this case, it is the address inputs which are changing, which of course is the case because we are increasing the number of memory locations. The hope is, we understand where these figures are uh, coming from. So we can just make that observation here, since that two memory locations are required, then we need 5 address address bus lines are needed. So how do we achieve this? Okay, so we can look at that. So once again, we have our 2 chips. If we determined we need 2, what we know is that we need 32 memory locations, and we have a chip with 16 memory locations. So of course, we'll need 2 such chips to achieve that 2 memory locations. So hence 2, that's the reason we need 2. So yes, we can indicate that. Once again, we have 16 by 4 chips. And each of those Once again, we have the control lines as well as the address lines and the input output lines. So we have input output lines at 4 for each of the chips. And then, because each of these is a 16 by 4, the address inputs are actually 4 for each of these chips. So once again, we have the 4 address lines. Yeah. Yeah, so I think that is okay. Then we have determined that our input output lines will be 4, for the resulting memory. So that means our data bus will be 4 lines. So we have the 4 lines of our data bus. This is the data bus. So these ones we can just wire them directly. You can get better straight lines than this. And then from our determination, we need 5 address lines, but we can see the chips actually have 4 address lines, but nonetheless, from our analysis, we need 5 address lines. We need 5. We need 5 address lines. So we have A4, A3, A2, A1, A0. So now our chips themselves actually have 4 address lines from A3 to A0, and for that one we can do the connections right away. So but now we are left with an address line here, A4. What do we do with that A4? This is our address bus. Anybody that can help us with what we do with the A4? Sorry, I saw somebody text. Make it a CS line. Yes, so that is correct. So remember, these chips will be storing distinct words So there is no common word that cuts across the two chips. So you will be reading words from these chips independently. So for example, for word, if we are using zero index, for words 0 to 15, they will be stored in the first RAM chip, RAM 0. And for the words 16 to 31, they will be stored in the RAM 1 chip. And therefore, if you want to read, the first 16 words, you just need to enable the first chip. You enable the first chip and disable the second chip. So that's why that address line will be essentially to control the chip select line. So for purposes of our labeling, we can indicate this as our chip select line, and this as our write enable chip select line, write enable. So we want to be able to chip select each of these chips independently using our A4 address line. So we can make this connection. We can make this connection to our chip select, and then what do we do we connect this? Sorry, do we connect this as such as well? Would that be useful? Anybody? Because if we connect it as such, we will not be able to select one and disable the other simultaneously. So what we need to do to be able to select one and disable the other, so we introduce a NOT gate. You can introduce a NOT gate in either of the two, but not both. So we can introduce the NOT gate here, such that at any given time, only one of the chips is enabled, and then the right enable, that one is we can connect it directly, just like in the previous case, because as long as the chip is not selected, it will have no impact. So it will only come into play if that particular chip is actually enabled. So this is our right. Yeah, so I think that is clear. And because we actually finishing this, we can just make a few observations, and then we stop. So we can, and this is something already you have seen here. So we can note that the upper address line that is A4 is used to select one RAM or the other, and this is via the a CS line. So the selected chip is the one that will be read from or written to. Then the other thing that we can note is when A4 is 0. When A4 is 0, which chip is enabled? When A is 0, which chip is enabled? When A4 is 0. Sorry?
RAM 0.
Yes, RAM 0. So when A4 equals 0, then the chip select line of RAM 0 enables the chip for read or write operations. And once that is done, any address location in RAM 0 can be accessed by A3 to A0. So that means the range of addresses representing locations in RAM 0 is, so we have A4, A3, A2, A1, A0. So the range of addresses, what we know is A4 has to be 0 to first select the chip. Then the memory locations within the chip can range from 00 to 11. So that is the range. Of course, so this is for RAM 0. I think we can. So the range of addresses representing locations in the two chips here. So this is for RAM 0, and for RAM 1. So for RAM 1, the first memory location will be what? Can somebody give us? It will be the first memory location.
1000.
1000 to
11111.
yes, to 1111. So this is for RAM 1. So as a conclusion, the total address range is 0002 1111. And this is actually 32 words, or 32 memory locations that can be stored. So we stop there. So we are done with with that particular session. So let's meet tomorrow in the afternoon for the CAT, and all the best.